Hello everyone, this is the first online lecture of Math 119. We're going to start from where we left off, namely section 4.4 extreme values. Before I start writing down some definitions, let me tell you why you're learning about this. If you're taking this calculus sequence 119, 120 or the other calculus sequence 117, 118, this means that in future, in whatever you're going to do, you will have to optimize or approximate functions of a single variable. Now the approximation part, that will be mostly done in 118 or 120. You're going to approximate values of certain integrals, you're going to approximate values of certain functions, and so on. The optimization part will be taken care of in all of these courses, 119, 117, 118, 120. In 118 and 120, you will learn how to optimize functions of several variables. But in order to be able to do that, you will first have to learn how to optimize a function of a single variable, and we're going to today cover that topic. So what do I mean by optimizing a function? I'm going to give you a function of a single variable and a certain domain, and then you will try to find the extreme values of that function. What do I mean by extreme values of a function? Let me write down some definitions. So let f be a function of a single variable and C be a point in the domain of f. Then f is said to have an absolute maximum. Instead of absolute, people sometimes say global maximum. At C if f of c is greater than or equal to f of x for all x in the domain of f. Okay, so absolute maximum means that at that point, like a function having its absolute maximum at a point means that the value of the function at that point is the largest possible value that it can take. Okay, so if f has absolute maximum at c, f of c is by definition greater than or equal to f of x for all x in the domain of f. Sometimes you don't want to find such points, but like this is very restrictive. Such things may not exist. Sometimes you're interested in points c where f of c is greater than or equal to f of x, not for all x, but for x that are around c. Okay, and if you just write down that definition, that gives you the definition of what's known as a local maximum. So let me write it over here. A local maximum at c, f set of a local maximum at c if f of c is greater than or equal to f of x for all x in a neighborhood for all x in a neighborhood of c that are in the domain of f. Okay, now when I say a neighborhood of c, what I mean is here's the number line, here is c. A neighborhood for you, a neighborhood is simply an open interval around c. Okay, so a neighborhood of c is something like this. It may be that like maybe c is the endpoint of an interval, c is the endpoint of the domain of f, in which case I can't consider one side. So when I say for all x in a neighborhood of C that are in the domain of F, what you do is you just take a neighborhood of C like this and you intersect it with the domain of F. Whatever you get, you just test for those x values, okay? So a neighborhood is simply any open interval around a C. Now, this gives you the notion of local maximum. You can see that any absolute maximum by definition is a local maximum, because if this inequality is true for all x, it's clearly true for all x in a neighborhood of C that are blah, 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 blah. On the other hand, the other direction is the other implication is not true, as we're going to see in a second. Let me write down two more definitions. Now, if you flip these inequalities, you get the notions of absolute minimum and local minimum. And everything is the same except you reverse inequalities, okay? Okay. So when I say extreme values of a function, I mean these, okay? These are called the extreme values of f. Okay. Now, let me draw a picture where I explain these notions. So that's fine. Let's draw such a picture. And let's say that I have a function y equals f of x, and this function is defined on the interval ab. Okay. Now, the absolute maximum of this function occurs at this point. Okay. So the absolute maximum of this function occurs at this point, which is also a local maximum by definition. But if you look at this point, you see this is not absolute maximum, because the value of the function at this point is less than the value of the function at this point. However, if you restrict yourself to a neighborhood of this point, if you restrict yourself to this little neighborhood, then in this little neighborhood, this is the largest value of the function. So this is a local maximum. Okay? And similarly, this point, like at this point, whatever it is, I have a local minimum, and the absolute minimum is over here. As you can see from this picture, not every local maximum is necessarily the absolute maximum. You can have infinitely many, like multiple local maximums. You can have infinitely many local maximums or minimums, and they need not be absolute maximums and absolute minimums. Okay? So, what next? Like I told you that you're learning about this because you want to optimize, like basically in future you will have a certain function, maybe the cost function, maybe something else, and you will have to optimize it. For example, if you have the cost function, you want to minimize the cost, okay, and you want to maximize the profit and so on. Like I'm going to give you these functions and you're going to try to find these values. But if you're searching for something non-existent, that might create a problem. Like, how do you know that these values exist at all? Now, if you remember one of the theorems that we covered in class when we learned about continuous functions, if f is a continuous function on a closed and bounded interval ab, then f has absolute extreme values. It has a maximum, it has while talking about maximums and minimums, if I don't specify an adjective for maximum, like if I don't say global or local, you're supposed to understand global. Okay, if I simply say a function is a maximum, you're supposed to understand a global. So f is an absolute maximum and minimum, an absolute minimum on AB. So we learned about this min-max theorem. So this theorem says that if you're working on a closed and bounded interval, and if your function is continuous, then absolute maximum and absolute minimum, they do exist. Okay, so you can actually try to optimize your function. So now that we know that, like, if we're working with such functions, continuous functions on closed and bounded intervals, these values exist. Let's try to learn let's try to find these values. How do you find these? So how do we find these? Okay. Now I'm gonna write down a theorem, in which I'm gonna also make some definitions. I'm gonna write down some definitions. So theorem. Okay. Let f be a function defined on some interval I, and suppose that f has an extreme value at some point C and I. Then, okay, so I have some function, like let's first understand the setting before I state the theorem. I have some function defined on an interval. This interval need not be a closed and bounded interval. It may be an open interval. It may be unbounded. It can extend to infinity. It's an interval, okay? And for some point C in that interval, I am assuming as hypothesis of theorem that my function f is an extreme value. I didn't specify what kind of extreme value it is. It may be a local minimum, local maximum, absolute minimum, absolute maximum. I don't care. If your function is an extreme value at a point, then there are three cases, okay, that can happen. So either C is a critical point of f. Now I'm gonna also make a definition, so let me write this in red. This is a critical point of f. What that means is this means it est. In Latin, it means that is. So when I say blah blah, that is blah blah. The second part is supposed to basically explain the first part. So C is a critical point of f. Now I'm going to define what a critical point is. A critical point of a function is a point where the derivative of that function takes the value 0. Okay. So this is the first case. If f is an extreme value at the point C, then C may be a critical point, or C may be a singular point. Now, what do I mean by singular point? I mean that f prime of C does not exist. So singular points are points where the derivative doesn't exist. So this is the second case. And the third case is C may be an endpoint. Like in the first two cases, I'm checking whether derivative exists or not, and if it exists, I'm checking whether it's 0 or not. But it is possible that I cannot check the derivative at all, because in order for derivative to be defined, at a point, that point has to be in the interior of the domain. So if it's the endpoint, you can't talk about the derivative. You can talk about right or left derivatives, but you can't talk about the derivative. So the third case says maybe I can't check the derivative because I'm at an endpoint. So this is the last case. C is an endpoint. An endpoint of the domain of F. Okay. Now, let me prove this theorem very quickly. So I want to say, like, I'm claiming that if F is an extreme value at a point C, one of these three cases happen. How do you show that A or B or C happens all the time? This is equivalent to, like, showing that A or B or C happens all the time is equivalent to showing that if a B or C do not happen, then A happens, okay? Those are the same thing. So I'm claiming that either the first case or second case or third case happens. This is the same thing as showing if the second two cases do not happen, then the first case has to happen, okay? These are logically equivalent. So let me do that. Okay. If suppose that a C is not an endpoint of the domain of F and F prime of C exists, okay? So I'm assuming that I'm not in the latter two cases, because if I am in the latter two cases, then I'm done. Like, I'm claiming that either the first case or the second case or the third case happens. If second and third cases happen, then that's fine. What I need to show is if they do not happen, then the first one has to happen. So I'm assuming that my point C is not an endpoint of the domain, which means that I can check whether the derivative exists or not, and I'm also assuming that derivative exists. Now, by a theorem that we proved earlier, if F has a maximum, if F has a local maximum or minimum at F prime of C and F prime of C exists, then F prime of C has to be 0. Okay, we proved this theorem earlier. Like, it's in the week when we proved mean value theorem. You can look at my lecture notes from earlier weeks to find this. We proved that if your function has a local has a maximum or minimum at a point, when I say maximum minimum, I mean, like, I can assume that it's a local maximum or minimum, it doesn't matter. So if your function is a local maximum or local minimum at a point, and if that point the derivative exists, then it has to be 0. Okay, so we proved this. There has to be a horizontal tangent line. We proved this earlier, and as a consequence of that, we get this nice theorem. Now, this theorem is very useful because it tells us what to do if we're trying to optimize continuous functions on closed and bounded intervals. It tells us that, okay, you have a continuous function on a closed and bounded interval. So the extreme values, absolute maximum and absolute minimum, they exist. Where are they? Well, there are three cases. They're either at critical points or singular points or endpoints. So this theorem simply tells me, it tells me my candidate points, okay? Let's see this theorem in action. So let me write down a very basic question. Example, okay. I should also tell you the following, because we are going to have recitation videos as well, just like the usual classes, in these lecture videos, I'm not going to solve that many questions. Like, I think I planned 5 questions for 4.4 this week. And in the recitation videos, you're going to solve a lot of questions, okay? So don't worry about me not solving that many questions in the lecture videos, because these are the lecture videos, okay? You're going to also have recitation videos thanks to our hardworking teaching assistants. Okay, what's the first question that I wrote over here? Okay, find if exists find the absolute extreme values of the function f of x equals 2x cubed minus 3x squared plus minus 12x plus 1, okay, on the interval minus 2 to 4. Okay, so I'm given a polynomial, a very simple function, a very nice function, and I'm given a closed and bounded interval. I want to find the absolute extreme values, okay? Later on, we're going to solve questions where we also find local extreme values, so don't worry about that for now. So the question says, if exists, find these guys. So the question actually has 2 parts. I should first decide whether they exist or not, and if they exist, I should find these, okay? First question. Do these values exist? The answer is yes. Why? Because polynomials are continuous. Okay? As f is a polynomial, it is continuous everywhere. And so on, it's also continuous on, like if it's continuous everywhere, it's continuous on this closed and bounded interval minus 2 to 4. Thus it has okay, this started not working. Yeah. Okay, this is embarrassing. In the middle of the video, like it's been how long has it been? 20 minutes? I think I need to change the batteries. Batteries of this, because this started not. Okay, it is working. Well, this was embarrassing. I just grabbed some batteries to replace, but then it started working. Anyway, I'm sorry. Thus, it has a absolute maximum and minimum on the interval minus 2, 4. Okay? Now, so I answered the first part of the question. This function, it does have absolute maximum and absolute minimum. Where at which points? This previous theorem tells me where to look. These are my candidate points. My candidate points are critical points, singular points, and endpoints. So I'm just going to check all these points. We have that f prime of x is, if you take the derivative of this function, you're going to get derivative of x cubed is 3x squared. So I have 6x squared there, and I have minus 6x, and I have minus 12 plus 0. So in 6 parentheses, I have x squared minus x minus 2, which factors as a x minus 2, x plus 1, I believe. Yes, factors like this. So this is the derivative of the function. So the critical points of f are so we get that the critical points of f are the critical points of f are, like, if you set this to 0, then either this factor is 0, this factor is 0, or this factor is 0, so you get x equals 2 or x equals minus 1. So I have two candidate points. Now, there are no singular points, okay? Singular points of f. There are no singular points because derivative of f is also a polynomial, which is defined everywhere. So there are none. And the endpoints of the domain of f, okay? Endpoints of the domain. Now, I'm given two endpoints. Well, I'm always given two endpoints. It's an interval. So I have two endpoints, -2 and 4, okay? So this theorem tells me that my absolute extreme values occur at some of these points, okay? So I should actually just check all these points. Now, you should be careful. This theorem works in one direction. It does not tell you that at every critical point you're going to have an absolute maximum or minimum. At every singular point you're going to have an absolute maximum minimum. It works in one direction. When the absolute maximum minimum occur, the points at which they occur are among these. But these are the candidate points. Not every candidate actually gives you an absolute extreme value, okay? So I'm just going to check all these points. So as f of -1 is, let's plug in -1 to this. Where's my function? Plug in -1 to this, you're going to get -2, a -3 plus 12 plus 1, you're going to get a 8, I guess. And plug in 2, you're going to get is 16 minus a 12 minus 24 plus 1. This is going to give you what? I have 4 minus 20 minus 19. And let's plug in -2. You're going to get a -16 and -12 plus 24 plus 1. I hope I'm not making an arithmetic mistake. A 28 minus 3. And the final point for a, you get 128 minus 48 minus 48 plus 1. So you get like 80 here, and then 32, 33. Okay. Now, which of these values is the biggest? This one. Which one is the smallest? This one. So f has its absolute maximum at 4 and its absolute minimum at 2, okay? So the absolute maximum minimum occur at a 4 and 2 respectively. Well, I'm talking about the absolute maximum and the absolute minimum because these values, if they exist, the value of the function, that's unique. On the other hand, it is possible that that maximum or minimum value occur at multiple places. So it could have been the case that at some other point other than 4, I also get the value 33, okay? So that would be fine. There can be multiple points at which your function attains its absolute maximum or absolute minimum. Okay, so let's go over this. So what did we do? We first showed that over here, this function does have absolute maximum and absolute minimum because it's a continuous function on a closed and bounded interval. And after observing that there are absolute extreme values, we used this theorem to find those. I know my candidate points. My candidate points are either critical points, singular points, or endpoints of the domain of f. So I took the derivative of f over here, and then I got two critical points. I have two endpoints of the domain of f, and I have no singular points. So I have 4 candidate points. I simply plug these into the function and try look at the corresponding values. The biggest one will be the absolute maximum. The smallest one will be the absolute minimum. Okay. So let's move on and solve another question where we are also going to have some singular points. Okay. So this time I'm not gonna say if exists. At the moment, like you know that if I give you a continuous function on a closed and bounded intervals, absolute max and absolute min will exist. So I'm just gonna simply say find the absolute maximum and minimum of this function f of x equals 2 cube root of x minus 1 squared minus x on the interval 0, 4. Okay. Now, as I said, for the because I didn't ask this time, you don't have to prove that the absolute minimum and absolute maximum do exist. But uh, if I had asked about that, you would say like, okay, this is a continuous function on this domain, and this is a closed and bounded domain, so it does have absolute maximum and absolute minimum. And now we will have to find these. So I need to check my candidate points, which are critical points, singular points, or endpoints of the domain of f. So I need to find the derivative of f. Now, let's differentiate this. In order to differentiate the first term, I need to use chain rule. So this is like 2 times composition of the cube root function with the function x minus 1 squared. So the outer function is cube root function. So what's the derivative of the cube root function? What's the derivative of the function t to the power 1/3? It is 1/3 times t to the power minus 2/3. So derivative of the outer function gives you x minus 1. Derivative of the outer function gives you 1/3 times blah blah to the power minus 2/3. And over here, like inside this, I have to keep whatever I had. So I have x minus 1 squared. And times, by chain rule, I have to multiply this with the derivative of the function inside, which is 2x minus 1. And over here, derivative of x is 1. Okay. So I am going to set this to a 0. I'm going to set this to 0. And if you set this to 0, that will simply give you the following. Now, if you write this down, this is going to like what's going to happen here is over here you're going to get minus 4/3, like x minus 1 raised to the power a minus 4/3, and then you can write it as x minus 1 to the power 1 over x minus 1 to the power 4/3, and times 2x minus 1. This will be equal to 1. I'm setting this equal to 0. I'm putting 1 on the other side, and I get this. And then this will give you a what? This will give you what? Now, this is the derivative, and if you set this to 0, you get this. Now, I'm going to multiply both sides by x minus 1 to the power 4/3, but in order to be able to do that, I need to know that this thing is not 0, okay? Well, okay, if it is 0, this is not defined anyway, so I'm just multiplying both sides by this term, and then I'm going to get 4x minus 1, 4 times x minus 1 equals a 3 times x minus 1 to the power 4/3, and then I am going to cancel this with this guy, and then this will give you 4/3 equals x minus 1 to the power 1/3, and from this you will get that x is a for thirds cubed plus 1. So I have one critical point. Okay, so this is my critical point. This is a critical point. It is actually the only critical point. It's a critical point. Okay. I also have one singular point. F prime does not exist at x equals 1. If you try to, like, you can see over here that you can't plug in 1 here, because when you try do that, you get 0 over 0, which is undetermined, so it's not defined. And if you actually write down the limit definition of derivative, the actual definition of derivative, and for x equals 1, if you try to compute f prime of 1, you'll see that it does not exist. So I have one point where I don't have derivative. So f prime does not exist at 1, so 1 is a singular point, okay? 1 is a singular point of f. And I have two endpoints, 0 and 4. 0 and 4 are the endpoints of the domain of f. So I got all my candidate points, critical points, singular points, the endpoints of the domain. Now I just plug in these guys into the function and see what I have. Okay. Oops. If you plug this in, you're going to get 2 times. You see, you subtract 1 from this and then square this. You're going to get cube root of 4 thirds cubed squared. And you're going to subtract this guy itself from this. So what's going to happen over here is these are going to cancel, and then you're going to get 16 over 9, and you multiply this with 2, 32 over 9, I guess, minus 64 divided by 27 minus 1, and this should give you a 96 minus 64 minus 27 divided by 27. If you just put these into common denominator, and this is what, 80, 91, 5 over, I think I got 5 over 27. Hopefully this is correct. If there are any computation mistakes which I miss, which probably is the case, like given how many arithmetic mistakes I do in class, I'm sorry for those. You can fix those, okay? Or you can put mean comments in the comment section regarding these. So this is the value of the function at the critical point. What about its value at the singular point? F of 1, if you plug in 1, you're going to get, this will be 0, you're going to get minus 1. You're going to get minus 1. And at the end points, 0 and 4, let's see. Okay. If you plug in 0, minus 1 squared is 1, its cube root is 1, so you're going to get 2 here. 2 minus 0 is 2. So you're going to get that. And if you plug in 4, you're going to get a 4 minus 3. 4 minus 1 is 3. 3 squared is 9. A cube root of 9. That's whatever it is. That's it. So you get 2 times cube root of 9 minus a 4. Okay. Now you can actually see that this is positive because like this is greater than cube root of 8. Okay. And cube root of 8 is 2. So if this were cube root of 8, you would have 2 times 2 minus 4, you would get 0. But this is bigger than cube root of 8, so this is actually positive. So why am I saying this? It's because of the following. I plugged in the candidate points. I'm searching for the maximum minimum value. So I actually have to be able to compare these values. This is positive. This is 5 over 27. This is 2. This is clearly the largest value. And this is the smallest one. Thus, f has its absolute maximum value a -1 at the point 1, and f has its absolute minimum value. It's the other way around. I'm sorry. Its maximum value is 2, and it occurs at 0, and its absolute minimum is -1, and it occurs at 1. So if you actually want, like, let me show you how this function looks on Mathematica. Okay, new document, plot. Okay, I can't click this for some unknown reason. Yes, 2 times, I'm gonna take the cube root of something. Okay, I'm gonna take the cube root of x minus 1 squared, and I'm gonna subtract x, and I'm interested in x values between 0 and 4. Okay, let's plot this. And this is the graph of the function, if you're interested. As you can see, I have a sharp corner at 1, which is why I have a singular point, like derivative at that point does not exist. Okay, like if you try to compute the right derivative, it's going to be plus infinity. If you try to compute the left derivative, it's going to be minus infinity. Okay, so derivative does not exist. So you have a singular point here, and this is 0. And as you can see, well, maybe I should zoom out. 0 is over here, but the point is, like at 0, it will take the value 2. Okay, maybe I should just plot this from -1 to 0. Yes, at point 0, it will take the value 2. So this is the maximum value, this is the minimum value, and it goes like this. Okay, so there is some critical point, which is this number, and it is somewhere over here. Like you're seeing that from this picture, there's some kind of tangent, there's some horizontal tangent line somewhere over here. So that will be a local maximum, okay, which we're going to talk about later when we learn about first derivative tests. So this is how the graph of this function looks like, okay? So at this point, I would ask whether there are any questions about how to find absolute maximum and absolute minimum of a continuous function in a closed and bounded interval, but there are no students, so I'm just gonna pretend that everyone understood everything and there are no questions. And if there are any questions, you should ask those during the virtual office hours that we're gonna hold, or okay, with the instructors and the teaching assistants. So let's see. I think 2 questions of this type are enough. So let's talk about something else, the first derivative test. Okay. The first derivative test. Now, so far, I told you how to find the absolute extreme values of a function, okay? Like, how did we do that? I mean, the theorem, this specific theorem, I did not specify what kind of extreme value I have here. I mean, this also works for local maximum and local minimum as well. But like, how are we making sure that we're searching for something that actually exists? We're working with continuous functions on closed and bounded intervals, and this guarantees that there is absolute maximum and absolute minimum. Okay, so far we learned how to find a absolute maximum, an absolute minimum of a function on a closed and bounded interval. But what if you're also interested in local extreme values. You can use the previous theorem as well. Local extreme values will also happen at critical points, endpoints, and so on. But there is one slight problem. Just by plugging in values, you can't actually figure out what kind of local extreme value you have. Like, let's take this example. These were your candidate points, and when you plug these values in, you get 4 values. If you're looking for absolute maximum and absolute minimum, well, the biggest one will be the absolute maximum, the smallest one will be the absolute minimum. I mean, that's obvious. But what if you're also looking for local maximum, local minimum? Can you tell me whether at this point my function has a local maximum or local minimum simply by looking at this value? I don't think so. I mean, the theorem does indeed hold for a local maximum, local minimum as well, this theorem, but the problem is simply plugging in the values will not tell you whether at that point you have a local maximum or local minimum. So this algorithm that I described, take the derivative, find the singular points, find the critical points, find the end points, list these, plug these in. Biggest one the biggest one is the absolute max, the smallest one is the absolute min. This algorithm won't work for local max or local min. So what do we do for these cases? We use the derivative tests. There are 2 of them, first derivative test and second derivative test. Second derivative test will be covered in a 4.5, so it's not going to be in this video. So let's learn about the first derivative test. So how does the first derivative test work? Okay, let f be a function which is continuous at a point C that is not an endpoint. Of f. If f prime of x is positive on some interval AC and f prime of x is negative on some interval ECB, then now let's I'm not going to write down the proof of this, so let's talk about the proof in words, and I'm not going to write it down to save some time. Okay, so I have a function which is continuous at this point, okay? And this point is not an endpoint of the domain of f. Endpoint of f, that doesn't make sense. Endpoint of the domain of f. So I'm assuming this is not an endpoint, which means that on both left and right of this point, my function is defined. Okay, that's fine. That's the setting. Now, pretend that on some open interval like this, AC, maybe I should draw it with red. All right, let me use other colors so it will be a colorful lecture. So pretend that on some interval like this, the derivative is positive. What does this mean? Remember, as a consequence of the mean value theorem, we learned that positive derivative means that your function is increasing. So over here, my function is increasing. And as hypothesis, I also have that f prime of x is negative on some interval of the form CB. Okay, that's like B. CB. So as hypothesis, I also have that over here, my derivative is negative. Negative derivative means that my function is decreasing over here. Well, it's increasing over here, decreasing over here, and it is continuous at this point. Okay, so what do you think will happen? you will have a local maximum, because if you take this interval AB, that will be a neighborhood of C, and in that neighborhood, on left of C, all the values will be less than f of C. On right of C, all the values will be less than f of C. And then f of C will be greater than or equal to f of x for all x in that neighborhood. Okay, so you will have a local maximum. F has a local maximum at C. Now, you can guess what happens if I flip these inequalities. Pretend that derivative is negative over here and derivative is positive over here. Then f has a local minimum this time. Okay? So, because of the same reasoning, if the derivative is negative here, then it's decreasing. And if the derivative is positive here, it's increasing. My function is continuous, so it's going to decrease. It's continuous, it's going to increase. There has to be a local minimum. Okay? So, I'm not going to write down the proof because I already told you the proof. This is the first derivative test. You can, like in this statement of this theorem, you may have realized that I took C as a point in the domain of f, which is not an endpoint of the domain of f. If C is an endpoint, you can come up with variations. So let me write that down. There are variations of this where one assumes that C is an endpoint of the domain of f. What do I mean by variations? Okay, let's pretend that C is a left-hand point of the domain of f, okay? That means that I can't check the derivative of f on left of C because C is the left-hand point. I can just go further left, which I guess is your right because the camera is like that. Sorry, I'm talking about my left. So, but I can check the derivative on the right. If the derivative is positive here on some interval, like this, then my function is increasing. And if my function is also continuous, then this endpoint has to be a local minimum. Okay? And if the derivative is negative here, this endpoint has to be a local maximum. And if it's a right-hand point, then everything will be flipped. Okay? So you can write these the variations down if you understood this, which means that I'm not going to write them down. So that's it. Let's put it over here. By the way, I'm gonna print this as a PDF, and it's not gonna be in the dark mode, which means that the background will be white and the writing will be black. And I'm gonna put these PDF files on the internet, so don't worry about these. So this is the first derivative test. Let's see the first derivative test in action. Okay. Example. Let's start with a polynomial. Find and classify all extreme values of f of x equals 3x to the power 4 minus 4 x cubed minus 72x squared on the interval. Okay, apparently I forgot to write down my interval. Let's make something up. Minus 3, 3. Okay. Solution. Now, let's read this question. We're supposed to find and classify extreme values. Finding extreme values, fine. That's fine. What do I mean by classifying extreme values? Remember, we have four types of extreme values. Let's go back to the very beginning. An extreme value is either an absolute max, absolute min, local max, local min. This question simply says find absolute max, absolute min, local max, local min of this function on this interval. Okay, so what do? We take the derivative. Okay, this is a calculus course. If you can't do anything, just take the derivative. It will tell you something. So let's take the derivative of this. A derivative of the first term is 12. Okay, something weird is happening with this pen. 12x cubed minus 12x squared minus 144x, and if you take this into 12x parentheses, you're going to get x squared minus x minus 12, which is going to factor as 12x times x minus 4x plus 3. And so the critical points no okay, I am sorry, it's been a tiring day. Classifying extreme values. Okay, what I mean is I want you to find and classify all critical points clearly. I mean, the other question can also make sense, but I don't want you to deal with the endpoints. I mean, I don't want to deal with endpoints myself, so I'm just going to say find and classify all critical points. Classifying critical points means you've tried to figure out whether those critical points give you a local maximum, local minimum, or maybe absolute maximum or absolute minimum, okay? So the critical points of f in this interval, I'm going to pretend that that interval was -3 and 5, not 4, 3. So the critical points of f in -3, 5 are. So I look at the critical, like what are the critical points? If I set this to 0, I get that x equals 0 or x equals 4 or x equals -3, okay? And let's actually change this to -5, 5, okay? I want to contain all my critical points inside. I am sorry for this. Like, I have a paper here where the question is written, but apparently I forgot to write down the interval, which is why this happened. Something embarrassing after the pen battery accident. So the critical points of f in this interval are 0, 4, and -3. Now I'm going to try to classify these. I'm going to try to figure out whether at these critical points I do see local maximum, local minimum. Okay? How do I do that? I'm going to create a table like this. And over here, I'm going to represent the x values. Over here, I'm going to represent f prime of x. And over here, I'm going to represent f of x. Okay? Now, the domain of this function is -5 to 5 during the question, so let me put -5 and 5 there. So I have three critical points, a -3, 0, and 4. At these points, the derivative takes the value 0, so I'm just going to put a 0 here. Okay? And then I will try to figure out the sign of the derivative. Why do I want to do that? Because if you look at the first derivative test, it tells you something about a local maximum, local minimum by looking at the sign of the derivative on the left of this local maximum and on the right of this local maximum. Okay. So in this interval -5 to -3, if you look at the sign of the derivative, let's see. In this interval, this term will be negative. Okay, this term will be negative. This term will be negative, and this term will be negative. Negative times negative times negative. This will be negative. On this interval -3 to 0, this term will be now positive. This will still be negative, and this will be negative. So negative, negative, positive. When you multiply these, you're going to get something positive. On this interval, this is positive, this is negative, this is positive, positive, negative, positive is going to be negative. And on this interval, a positive, 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 everything is positive. Now, over here, because I have negative derivative, my function is decreasing. Over here it's increasing. Over here it's decreasing again. Over here it's increasing again. So by the first derivative test, at this point, I do see a local minimum. And over here, I do see another local minimum because the derivative is negative and positive here, negative and positive here. And at this point, I have a local maximum, okay? So f has a local minimum at x equals a -3 and x equals 4, and f has a local maximum at x equals 0. If I want to find all the extreme values of f, what I would do is I would just plug these numbers into this function, okay? And I would also plug in the endpoints. Then I would get 5 values. The biggest one will be the absolute maximum. The smallest one will be the absolute minimum, okay? And I said find and classify all critical points, which means that I'm not interested in endpoints. But if someone asked you, like at the endpoint 5, do you have a local max or local min? Let's see. This function is increasing, and then it's going to stop here. So at this point, you also have a local maximum, and over here it's decreasing, starting from -5. So at this point, you have a local maximum as well. But I'm not interested in endpoints. Like I wrote the question so that I'm just interested in critical points. The point of this question was to show you how to use the first derivative test. Okay. So for the little mistakes I'm making, so many modifications in the question. Let's move on to another question where we see the first derivative test in action. Example. So another question which involves the first derivative test. Okay. So yes, find the local extreme values of f of x equals x minus a cube root of x squared. Okay, this is a question from your book actually. It's a nice question on the interval -1 to 2. Okay. Now I change the phrasing of the question. I don't say find and classify the critical points, because in this question we will also have actually a singular point. Okay. So the question is find the local extreme values of f. Okay. Solution. So let me take the derivative of this. We have that f prime of x is 1 minus. Now, if you take the derivative of this term, you're going to get 1/3 times x squared to the power -2/3 times derivative of inside is 2x. So you're going to get 1 minus 2x divided by 3x to the power 4/3. Okay. Now this is derivative, so a f has a singular point at x equals 0. As you can see, you can't plug in 0 because it makes this undefined. Even though 0 is in the domain of this function, it makes the derivative undefined. And if you write down the limit definition of a derivative and try, check what f prime of 0 is, you'll see that it doesn't exist. Okay, so you wear a single point at 0, and the critical points of f are, let's say, if you set this to 0, you're going to get 1 equals 2x divided by 3x to the power 4/3, and then you can multiply both sides by this guy, which is fine. And because 0 is a singular point, I already know that I can't plug in 0, so I can cancel these because these are non-zero. Then this gives you x to the power 1/3 is 2/3, so you get that x is 8/27. So the critical point of f, there's only one, is 8/27 as this happens. Okay. Now, we want to figure out local extreme values. And first derivative test is a useful tool. So let's try that. Now my interval is -1, 2, and I have a one singular point here, 0, and I have one critical point, 8/27. Now, at 0, my derivative is undefined, okay? And like when people draw these tables, they put this double line to denote that that's a singular point, the derivative doesn't exist there. And at 8/27, my derivative is 0, okay? And this is the other endpoint. Okay, and I have my f here. Now, I'm going to figure out the sign of the derivative in these intervals. Between -1 and 0, let's see what happens here. This is in this interval, x is different than 0, so I can cancel these. When you cancel these, you're going to get 1 minus 2 over 3x to the power 1/3. And in this interval, this will be negative. Because of this minus, this will be positive. So in my derivative is positive here. In this interval, you can actually check that it will be negative. Okay, just give me a second. Yes, it will be negative. You can simply plug in some number like 1/27 to see whether this is a positive or negative. And over here, it will be a positive as well. Okay, so my function will increase, decrease, and increase again. So f has a local maximum at x equals, let's say, it's increasing, decreasing. Over here, it's a local maximum. But I didn't ask for just local extreme values at critical points. In the previous question, I was interested in just the critical points. Okay, but over here, I'm asking for all extreme values on all of this interval. So I have to consider the endpoints as well. So over here, like my function is increasing and it stops here. So this it's gonna look like that or this or like that. In all these cases, my function will have a local maximum there. Okay, so I have a local maximum at x equals 0 and x equals 2, and f has a local minimum at this point by the first derivative test. And you see, starting from -1, my function starts increasing, which means that this is a local minimum. Okay, these are like a, you get that this is a local minimum and this is a local maximum by variations of the first derivative test I told you about. So I have two local minimums at these points. Okay, so these are the local extreme values. And if you want, I can figure out the absolute maximum and absolute minimum as well. How? Well, plug these in. Plug -1, 0, 8 over 27, 2. The biggest one will be the absolute maximum. The smallest one will give you the absolute minimum. Okay? But I'm not asked that in this question. So, what have we done so far? Let's do a recap, and then we're going to start the final part of section 4.4. We defined what it means for a function to have an extreme value at a point. We defined 4 types of extreme values. And then we realized that we learned before when we covered the min-max theorem while covering continuity that the existence of absolute maximum and absolute minimum are guaranteed by the assumption that f is continuous on a closed and bounded interval. And then we focused on how to find these. How do you find absolute maximum and absolute minimum on a closed and bounded interval? Well, we stated this theorem which told us that if you have an extreme value, which may be local or global, it doesn't matter, at a point, then that point is either an endpoint of the domain of your interval, or it's a singular point where there does not exist. And if it's not an endpoint, and if it's not a singular point, so if it's inside your interval and if the derivative exists, then the derivative has to be 0. So it has to be a critical point. So I have my candidate points: critical points, singular points, endpoints. And then we solved 2 questions where we're given a continuous function and closed and bounded intervals. We find these candidate points, we plug these in, and we look for the biggest and the smallest value among these. Okay, and those are the absolute max and absolute min. And then we realized that this strategy, this algorithm, won't work if I want to find local extreme values. So for that, we had to develop another tool, which is the first derivative test. The first derivative test tells you whether you have a local maximum or a local minimum at a point by looking at the sign of the derivative on the left of that point and on the right of that point. If on the left of that point your derivative is positive, your function is increasing. If on the right the derivative is negative, then it's decreasing, so you have a local maximum. And if on the left it's negative, your function is decreasing. If on the right it's positive, it's increasing, so you have a local minimum. Okay? And by the way, this point need not be a critical point in the statement of the first derivative test. Like something like this can happen. Something like this can happen. This may be your C. So over here, the derivative is positive. Over here, the derivative is negative. And this is a continuous function. So C is the local maximum. So the C need not be like, as you can see, I don't make the assumption that this C is a critical point. It's just a point. And using the first derivative test in this question, we classified the critical points of a function on an interval. What you do is you take the derivative, find the critical points, then you do this table on which you write the sign of the derivative, and then using this signs you can figure out the behavior of the function, and then from this behavior you can figure out by first derivative test whether you have a local maximum or a local minimum. Okay. And we solved another question like this, in which we also considered the endpoints, because you can have a local extreme values at endpoints. Okay. Now, if you may have realized that in all these questions, I dealt with continuous functions on closed and bounded intervals, because in this case, absolute maximum and absolute minimum they do exist. Like this is a nice setting. If you have continuous functions on closed and bounded intervals, everything works nice. But what if you don't have a closed interval, but you rather have an open interval, which in practice you will have a lot, okay, frequently. Like not everything works as in the books. In practice, when you actually try to use this, you will end up having to have open intervals and you will need to optimize a function on an open interval. What do you do? First of all, you have to be very careful because the absolute max and absolute min may not exist. Okay, we've seen examples of this before when we covered the min-max theorem. For example, if you look at the function y equals 1 over x on the interval 0 infinity, there is no absolute max and there is no absolute minimum. Please do not say that 0 is the absolute minimum. This function, as x goes to infinity, approaches to 0, but it does not take the value 0. So 0 is not an absolute minimum of this function. It's the limit of this function at infinity, but it is not its absolute minimum. So for this function, there's no absolute minimum, there's no absolute maximum. And you need like I'm not going to give any other example to illustrate this phenomenon. So these things may happen. So you have to be careful when you are given open intervals. Okay, I think this is running out of battery, this time computer. So I'm just going to grab, I am just going to grab this monitor. This looks so amateur, I'm sorry. And actually, this is the first time I'm lecturing like this using a tablet, so excuse the unprofessionality, okay? So what do you do when you have open intervals? Unlike the previous case, there is no single algorithm this time. You have to come up with ad hoc methods specific for each type of question. Though there are some made up theorems which are specifically made up to cover certain cases that actually happen in real life. I'm going to cover one of these, which is also in your book. So the question is, what do we do? What do we do if we have open intervals? Okay. Theorem. Let f be continuous on AB where I allow these A and B to be infinities. The statement of the theorem is suppose that I need some hypothesis. Suppose that the right limit of f at A is a L and the left limit of f at B is M. Now, if for some u, if for some u in AB, f of u is bigger than L and M, then f does have an absolute maximum on the interval absolute maximum on the interval AB. And similarly, I'm just going to flip these inequalities. Then instead of having an absolute maximum, f will have an absolute minimum. Okay. Just give me a second to check something. Okay. Now let me prove this. At the moment, the statement might look confusing to you. When I write down the proof, everything will make sense. This is like as I said, this term is made up to cover many cases that you're in practice, but it's not going to cover definitely all the cases that you'll see. So let's say that let's read the theorem. Let's look at the setting. I have a continuous function on an open interval a b this time. So I have an open interval a b. Okay. So my function has a right limit at a, and it's called L. Okay. And it has a left limit at b, which is called m. Okay. And my function is continuous on this open interval. The first part says, pretend that for some point u in this open interval, f of u is greater than both L and m. So somewhere my function takes some value which is bigger than these guys. Then the theorem says that you have to have an absolute maximum. And here is the reason. So let's name this A, let's name this B, and let's prove this is proof of A. Let's prove this. Since suppose that there is some u, suppose that there is some u such that there is u and AB such that a f of u is greater than L and m. Then there are a x1 and x2 such that a f of x is less than f of u for all x between a and x1, and f of x is less than f of u for all a x between x2 and b. Now, if by this assumption, when x approaches to a, f of x approaches to L. L is strictly less than f of u, okay? L is strictly less than f of u, which means that at some point, there will be some point. Maybe I shouldn't have drawn my graph like this. Let me draw some other graph. Okay, good. This is better. As x approaches to a from right, f of x approaches to L, and L is strictly less than f of u, which means that there is some point, let's choose this, x1, such that on left of x1, f of x is always less than f of u. So I can take such a point. And similarly, because the left limit of f at b is m, and m is strictly less than f of u, if you get sufficiently close to b, there will be some point x2 on the right of which all the values will be strictly less than f of u. Okay? Now, as f is continuous on, okay, let me change the picture again, like without playing with this much. This is fine. This still works, okay? On right of x2, the values are less than a f of u, and on left of x1, the values are still less than f of u. So f is continuous on the closed and bounded interval x1, x2 because it's continuous on the whole open interval. F does have an absolute max on x1, x2, say at a c, okay? So because this is a closed and bounded interval and f is continuous, f does have an absolute maximum. So let's say that it does have an absolute maximum at this point, c. Clearly, f of c is greater than or equal to f of x. By definition, for all x in the interval x1, x2, closed interval x1, x2, f of x is less than or equal to f of c. But we also have that f of c is greater than f of u, greater than or equal to f of u. Why? Because f of u is in this interval x1, x2, okay? I mean, I can make that happen. I forgot to write that. There are x1, x2 such that this actually contains u. Now, this is by the assumption that f of c is greater than or equal to f of x for all x in this interval, but f of u is greater than f of x for all x between a and x1 and for all x between x2 and b. But now look what I have here. F of c is greater than or equal to f of x for all x in this interval, but it's greater than all f of x for all x in the remaining parts. Thus, f of c is greater than f of x for all x in the interval ab. So f does have an absolute maximum at c. So I have proven that on this open interval, if this happens, I do have an absolute maximum. And the proof of part B for minimum case is similar. Okay, now we're going to see this theorem in action. Let me look at what I want to do. Okay, I want to consider the following function. Let f of x be the map x squared plus 54 divided by x plus 5 on the interval blah blah be defined on 0 infinity. Show that f has an absolute minimum on 0 infinity and find this value. Okay. So what do we do? Let me first show you how this function looks. Like, this is gonna be cheating. Like, before doing anything, I actually am I'm kind of showing you how this function looks, but that's fine. I don't want that. Let's plot x squared plus 54 divided by x plus 5. And let's plot this from 0 to 100. I can't go up to infinity, clearly. That's bad. 6. That's too low. Okay. Maybe 20 will work. Good. This is the graph of this function. Now, from the picture, you can actually see that there has to be like there's an absolute minimum. But clearly, referring to a picture is not a mathematical proof. So we're gonna prove this. But I'm trying to show you why you should have an absolute minimum from the picture. When x tends to infinity, what happens to this function? It goes to infinity. When x tends to 0 from right, what happens to this function? It also goes to infinity. So over here it goes to infinity, over here it goes to infinity, it is continuous, okay? So somewhere in between, there has to be an absolute minimum, okay? Now let me argue this using the theorem we just stated. Clearly, yes, clearly, a limit of f at infinity is infinity, and limit of f at 0 from right is, when x tends to 0 from right, this term goes to 0, this term goes to 5. Well, 1 over x goes to plus infinity. You multiply it by 54, that's fine, it's going to go to plus infinity. So if you just go back to the setting, what's happening is, in that question, my a is 0, my b is infinity, and these limits both turned out to be infinity, which means that this condition will be automatically satisfied because f of u will be less than infinity, okay, for any u. And then this theorem will guarantee that there's an absolute minimum. Clearly, blah, blah, blah. And the value of this function is less than infinity for all x. Thus, by the theorem above, f does have an absolute minimum on the interval 0 infinity. Now let's figure out where it is. We have that f prime of x is 2x minus 54 divided by x squared. Derivative of x squared is 2x. Derivative of 1 over x is minus 1 over x squared. So I have 54 there, so I have this. And derivative of 5 is 0. So if you set this to 0, you get that 2x is a 54 divided by x squared. So that means that 2x cubed is 54, which means that x cubed is 27. So x is 3. Okay, so I have a critical point. I also have one singular point, which is 0, but the problem is 0 is already not in the domain of this function, so I don't have to consider that a singular point. So this is my table now. It goes from 0 to infinity, so I'm just going to leave this part open. This is my x values, prime of x, and at 3 I do have a horizontal tangent line. My derivative is 0. Now, on left of this, let's plug in 1 here. If you plug in 1, you're going to get 2 minus 54. You're going to get something negative. So it's going to be take negative values over here. Over here, it's going to take positive values. So my function is decreasing and increasing. Okay? Now, let's think about this. As f prime of x is negative on 0 to 3, and f is continuous on the interval 0 to 3. Now this time I write 3 closed. F of x is less than or equal to f of 3 for all x less than or equal to 3. for all x between 0 and 3, 3 included. Okay. Well, I don't have to include 3. Why? Okay. You have negative derivative, which means that your function is decreasing. Okay, like from the picture, it's obvious. But let me actually prove this. Pretend that f of x were bigger than f of 3. Then what would you have? Put this to the other side. Divide by a, okay, this would be positive. And divide by x minus 3. Now, if x is less than 3, this will be negative, so this would flip. Okay? Now, wait, what? What am I doing? F of x. Oh, this is already false. F of x is bigger than equal to f of 3. I am sorry. I'm trying to prove this, not the other one. Like, because if x is on the left of 3, it's supposed to take bigger values. But let's actually, like, let me prove this very quickly over here. Like, you don't have to do this. I just want to do this to remind you the mean value theorem. Suppose that f of x is less than f of 3. Okay? Then f of x minus f of 3 would also be negative. If you put this to the left hand side, this would be less than 0. But if you divide this by x minus 3, and if you assume that x is less than 3, this is negative, this quotient will be positive. And by the mean value theorem, you see, mean value theorem tells you that this is equal to f of c for some c between x and 3. Okay? So if you assume that f of x is less than f of 3 and x is less than 3, then you get that this quotient is positive, but by mean value theorem, this quotient is f prime of c for some c between x and 3. But then I assume that the derivative is negative, but then I get the derivative is positive. So if I assume that f of x is less than f of 3, I get a contradiction. I get something absurd, which means that f of x is greater than equal to f of 3. And similarly, you can show that f of x is greater than equal to f of 3 for all x between 3 and infinity. Thus, f of 3 is less than or equal to f of x for all x between 0 and infinity. And so f does have an absolute minimum at 3, at x equals 3. Okay, now you can show by a similar argument that f of x is greater than or equal to f of 3 for all x between 3 and infinity, because on this part the derivative is positive. If you assume that this is not true, by mean value theorem you will get negative derivative. Okay, and then what do you get? F of x is greater than or equal to f of 3 for all x between 0 and 3, but this is also true for all x between 3 and infinity. So this is actually true for all x between 0 and infinity, because f of 3 is less than or equal to f of 3. So f of 3 is the minimum value of this function, which means that it is the absolute minimum. Now, one thing that I want to mention, I could have actually, like, the question is show that f is an absolute minimum and then find this value. I pretended as if this question has two parts. Okay, first show that it's an absolute minimum, then find it. I could have simply done the second one. If I prove that blah blah is the absolute minimum, it will automatically show that it exists. So only the second part of this question this would actually, this part of the question, this part uh, would actually suffice, because this part already proves that there is an absolute minimum by simply finding the absolute minimum. Okay, but if I did that, you would probably ask, well, then why did we cover this theorem? Okay, this seems pointless. So I just wanted you to see this theorem in action. So what I did is I did some redundant steps. I first showed that there's an absolute minimum using the theorem, even though I didn't have to do that. And then I found the absolute minimum by actually picking out a candidate point and then proving that that candidate point, at that candidate point, I actually do have an absolute minimum. Okay. So this is an example where we have an absolute minimum of a function on an open interval. I may want to do one more question for this. Do I want to do that? Let's see. Okay, I think I'm going to stop now. The reason is we're not done with these tables and local max and absolute min and so on. In the next section in 4.5, when we learn about concavity and inflection points, I will also be doing tables and for second derivative, and within those tables I will also like put the first derivative as well, and I will also talk about local max and local min, even though I don't have to. Why are we all doing this? Because in the section after 4.5 we will learn how to sketch the graph of a function, and I'm going to give you an algorithm, and the first two parts of the algorithm will be find and classify the locally extreme values, find and classify find inflection points, and find the concavity of your function. So the point is, on closed or open intervals, it doesn't matter. We will be doing these over and over again in future. So I don't think it's necessary for me to solve another question where we optimize a function on an open interval, because like we will be doing this implicitly when we sketch graphs of functions. Before I end the lecture, let me show you the graphs of some functions that we dealt with today. I forgot to actually show you the graph of this, so let me do that on Mathematica. We want x minus I think I have this. This program is Mathematica, and our university has a license for this. And as university affiliated students, you can actually download this by connecting to the university's software website through VPN. So try that. Like, this is a nice software, and we were dealing with some -1 to 2. So let me plot this. Yes. This is the graph of, remember this function x minus cube root of x squared on the interval -1, 2. Remember, like I had this table. This was a singular point. My function was increasing, decreasing, and increasing again. Here is this graph, increasing, decreasing, and over here at the point 8/27, which is somewhere over here, you see a horizontal tangent line. Okay. Like my function is decreasing up to that point, and then after that it starts increasing again. Okay, so this is the graph of this function, and as you can see, let me make this smaller. This point, this left-hand point, is a local minimum. This right-hand point is a local maximum, and I have a local minimum here, and I have a local maximum here. Okay, and let me show you this one as well. Let me show you this one as well. 3x to the power 4, power 4 power 3, minus 72x squared, minus 72x squared. on the interval -5 to 5. This is the graph of the function. By the way, as I said, we will learn how to sketch graphs, so you don't have to use Mathematica. I'm just showing you these so that like this, like you don't see any pictures here. I can perfectly get these answers without drawing any pictures just by looking at these tables. But if I show you the graphs of these functions, it will make more sense. So let's look at this. I see a local maximum here, I see a local maximum at 0, and I see a local maximum here. And we had a local maximum here, but this question didn't ask about endpoints, so I ignored that. We have a local maximum at 0, and we have a local maximum over here. So my function is decreasing, increasing, decreasing, increasing. So decreasing, increasing, decreasing, increasing. And this point is -3, as you can see, and this point is a 4, as oops, you can see. I think I accidentally closed the OneNote. Okay, sorry, like because this is the first lecture, I am apologizing to everyone for all the unprofessional things that happened throughout, like me trying to change the battery, me actually plugging in an adapter for the computer and the stuff. Okay, and I think that's it for this lecture. Uh, expect more videos of the following lectures. Okay, stay safe.